Good morning all, I am Joyeta Moietree and yes, I am back with my fourth video on thermal physics, and today's chapter is basically melting and boiling. Alright, so at the beginning of today's video, I want you to face a different situation. So basically the situation we face at the beginning of today's video is supplying heat does not change the temperature of the object. So in our last video on heat capacity, we basically learned when we supply heat and then we calculate the heat, all these things. Now in this video, we are going to face a different situation, that is supplying heat does not change the temperature of the object. That is so disrespectful. I mean, heat is supplied, heat is absorbed, but temperature is not changing. That is just so disrespectful. But anyways, due to this disrespectful behavior of matter, the formula Q equals to mc del theta gets invalid. So basically, Q equals to mc del theta is dead. So Q equals to mc del theta becomes invalid. Now ask why. Of course, come on. What does del theta stand for? Del theta stands for difference in temperature. So if there is no temperature change, how will be there a difference in temperature? And heat is supplied, the temperature does not change. It does not mean that heat is not absorbed. As I said, heat is absorbed. So now, you must be thinking that did I just make this situation up, or this sort of situation actually exists? Well, you can actually find out if you think wisely, because think about change of state. What happens during state change when solid changes to liquid, liquid changes to gas, and then vice versa, all these things? Temperature does not change. When solid changes to liquid or liquid changes to gas or vice versa, during that time, temperature does not change. So we get fact which we already knew, that temperature does not change during state change. So heat is absorbed, state change is occurring, but temperature change is not occurring, and we already lost one of our important formula, that is Q equals to mc del theta. So how are we going to calculate heat? Well, does it look like that solids, liquids and gas, they care about this thing, that this Q equals to mc del theta, it's invalid now? They don't. What's the problem if one formula gets invalid? They will bring in a new formula, right? Well, even if teenagers are not steady with their words, solids, liquids and gas, they are not teenagers, so they are steady with their words. And since they have said that they will bring a new formula, they will. So we meet a new formula, that is Q equals to ml, which will only be used during state change. So we know Q equals to heat, m is mass, and L over here is a new term which is specific latent heat. So before we move into the mathematical definition of latent heat, we will first identify its unit, which is pretty easy. So if you make L the subject, then you have Q by M, and the unit of Q, which is heat, is joule, and the unit of M, which is mass, is kg. So you have joule over here and you have kg over here. So it is pretty obvious that the unit of specific latent heat will be joules per kg. So yes, we know the unit of specific latent heat. Now we are in a phase of finding its definition, mathematical definition. Well, other than mathematical definition, we know that specific latent heat is basically the property, but we always need to know the mathematical definition. So, as you can see, we have L equals to Q by M. This entire thing remains pretty same, just the naming changes. So we face here two terms, that is LF and LV. Alright, the equations remain same, Q equals to ml. Basically the L either gets replaced with LF or LV depending upon the situation. Now let me explain it to you in more detail. That is, suppose when melting occurs, alright, I know all of you know this, but again for you to revise, I am repeating this, that when solid changes to liquid, it is called melting. When liquid changes to gas, it is called boiling. When gas changes to liquid, it is called condensation. And when liquid changes to solid, it is called freezing. I know all of you know it very well, but just for you to revise. Alright, so during melting or freezing, whatever, basically when solid changes to liquid, this change takes place between solid and liquid. That time it is called latent heat of fusion. Basically, LF stands for latent heat of fusion. So LF replaces L. So when the state of change occurs between solid and liquid, we use the formula Q equals to mLF. And LF stands for latent heat of fusion. Alright. And this is pretty obvious that when state change occurs between liquid and gas, we replace it as Q equals to mLV. Now what does LV stands for? LV stands for latent heat of vaporization. So yes, we are basically now pretty much acquainted with the two terms LF and LV. And as we know now that this LF basically replaces L or LV replaces L. Other than that, it's no different equation. So if we try to find a mathematical formula from this equation, we will probably be successful. Alright, so let's see, what do we do to find the mathematical formula? We will consider mass as 1, so 1 kg. So now let's say imagine we have LF over here. So if you make LF the subject, it's the same, LF equals to Q by M. And if you consider M as 1, so 1 kg. Now we have over here heat. Now we know heat is needed, but for what? Well, that is very easy. What did I say? Latent heat of vaporization, basically, it is only used during the state change between solid and liquid. So the mathematical definition of latent heat of fusion will be the amount of heat needed for a solid to change into liquid of mass 1 kg. Alright, and latent heat of vaporization is also pretty similar. That is, latent heat of vaporization is the amount of heat needed for a liquid to change to gas of mass 1 kg. So yes, we have now got our formulas and our mathematical definitions. Yes, so what do we need now? Are we done? Well, no, as you know already that I am not done so easily, so unfortunately I will speak more. I'm sorry for that. But then basically, how many of you have wondered that why this entire thing takes place? At the first place, why did we cancel MC del theta? Because there is no del theta, no change in temperature, and then we bring a new formula. That is not a big deal. New formula is new formula, but why is there no change in temperature? Anyone? Why is there no change in temperature during state change? Well, let me answer it on behalf of you because I always do. Alright, so basically what happens is during state change, we understand that solids, liquids and gas, each of them individually have certain different molecular arrangement, which we already have studied in the first video of thermal physics. That is the different molecular arrangement of solids, liquids and gas. Now what happens is, when they get heat, when they basically change their state, they need to change the molecular arrangement. So when they get heat, the heat is not used to change the temperature. It is used to change the molecular arrangement and basically shape the molecular arrangement in a way of the state of matter that they're changing to. Suppose a solid will change into liquid, so when the state change will occur, basically when the heat will be absorbed and no temperature change will take place, and this molecular arrangement of solid will be changed to the molecular arrangement of liquid, and then basically a solid melts to liquid. That is when it is said. So it is all about the molecular arrangement, right? So I think now you may think that, oh, we understand so well, this is so deep, but let me say you, it is not so deep, and we did not understand it so well till now, because although we understand why there is no temperature change and all these things, we basically understand these equations and stuff, but we don't understand the full thing. Ask why? Because we basically know now two contrasts of situation. One is, okay, temperature change will take place, and then we have this memorized instinct that when temperature change takes place, mc del theta, okay, this equation. And during state change, Q equals to ml. Alright, done. But these two events are actually happening together, right? It's not just the two events from two different planets, that in this planet this thing will occur, in this planet this thing will occur. No, these things are basically occurring around us all the time. So these two events, they are linked. So how are we going to understand that at this point state change will take place? Other than that, there will be no, basically state change will not take place. So these things, how are we going to understand? Well, when state change, the term state change comes in, a more well-known term comes in our mind, that is melting point and boiling point. So basically, when a substance reaches to its melting point or boiling point, that is when the state change occurs. Now, what is melting point and boiling point? For you to revise, that is, melting point is the temperature at which a solid changes to liquid, and boiling point is the temperature at which a liquid changes to gas. So when this temperature of a certain substance is reached, that time the state change of that individual substance occurs. Alright, so I think our doubts are getting cleared slowly, but not really. So what I have done is, I have planned to explain you this entire situation involving both the formulas, Q equals to mc del theta and Q equals to ml, because I personally think that it is important to understand the entire series of scenario rather than just memorizing this situation, this formula, in that situation, that formula. So wait a minute, I will bring you something. Alright, so wait for a while. Alright, so basically I have chosen a substance called water. So we all know the melting point and boiling point of water. That is, the melting point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. So we know now that at 0 degrees Celsius and 100 degrees Celsius, state change of water will take place. And we also know the name of the three states of water, that is ice, water and vapor. Alright, so basically, since we know it, let's finally introduce you to this. And let me remind you something, that is, as I've said, that state change will take place at 0 degree and 100 degrees Celsius. It's not always for every liquid. For you to remind, don't just think that, okay, state change will occur at 0 degree and 100 degrees Celsius. No, state change will occur at the melting point or boiling point of the liquid you are working with. So let's get started. So first, as what we always do, we always observe. Let's do our observation. What is here? Well, I can see 6 circles but not really circles, and I can also see that there are 5 kg marks in each of them. And what else can I see? Well, one important thing I can see is, as you can see, it is Q written, so heat is supplied to this substance, and this heat is actually transferred from one substance to another, and like this way. So of course I have done it just to show you the heat transfer thing. Basically heat transfer is not important, it's that heat is given to them. That is the thing. In reality, of course, some heat will be lost. Each and every heat, like all the heat won't be transferred to the next substance. Some heat is of course still lost to the surrounding, but I have not considered that because my main motive is to explain you this, not heat loss to the surroundings. Alright, and one last thing that we can observe is there are different temperature markings in different substances, if you can look. And another thing is there are different symbols written. I can see S over here, L over here, G over here. So basically, for your understanding, S stands for solid, L stands for liquid, and G, of course, gas. Alright, so since we are done with our observation, let's finally start working. So what we basically have to do with this thing is, they are showing us a scenario. We have to write down the formula that we will use to calculate the heat at these arrows. These are basically heat is giving away this heat. So we will basically calculate the heat, and we have to name the formula that we will use to calculate heat. Alright, so let's see. We have 5 kg ice, which is solid, at minus 50 degrees Celsius, and which is changing to 5 kg ice, which is solid, at 0 degrees Celsius. So what formula are we supposed to use? What? Q equals to ml. MLF. No, it's wrong. You see, I understand, as I have said, that the melting point of water is 0 degrees Celsius. So at 0 degrees Celsius, the ice will change to water. But before it reaches to 0 degrees Celsius, some heat is actually used. Some heat is actually basically needed to change the temperature and take it to 0 degrees Celsius, right? If the temperature does not reach 0 degrees Celsius, how will melting occur? So if you look at it more closely, it is 5 kg ice which is solid. It is still 5 kg ice which is solid. This is at minus 50 degrees Celsius. This is at 0 degrees Celsius. Temperature changes take place and state change is not occurring. So now we can understand that Q equals to mc del theta. But still it seems a little confusing that despite it is 0 degrees Celsius, why will mc del theta be used? You see, my dear, let me explain it to you in more detail. That is, 0 degrees Celsius is the melting point of water. So at 0 degrees Celsius, the ice will change to water. But the temperature of ice is at minus 50 degrees Celsius. So at first, some heat is needed to rise the temperature and take it to 0 degrees Celsius. When the temperature reaches 0 degrees Celsius, from that time onwards, state change will take place. But we are working with a time limit when minus 50 degrees Celsius is changed to 0 degrees Celsius. So we can see that the ice, it is still solid and temperature change is occurring. So of course, Q equals to mc del theta. And one more thing. This C over here, that is specific heat capacity, the specific heat, the C will be of ice. It will not be of water, it will be of ice, because this amount of ice of this temperature is changing to this amount of ice of this temperature. So it will be Q equals to mc del theta, the specific heat capacity will be of ice. Alright, now we have finally the melting situation. You see 5 kg ice which is solid is changing to 5 kg ice which is liquid, state change is occurring. And 5 kg ice solid is at 0 degrees Celsius, 5 kg water liquid is at 0 degrees Celsius. So no temperature change and state change is occurring. So of course Q equals to ml, and this time since it is melting, so mlf. So Q equals to mlf, where latent heat of fusion will be of water. Sorry, latent heat of fusion will be of ice, because this amount of ice is changing, is melting to this amount of water. So the heat given is basically from ice. So that's why latent heat of fusion is of ice. We will meet scenarios when the specific heat capacity will be of water, or other things will be of water, but you have to first understand. How will you understand that this specific heat capacity of latent heat, it is of that ice or water, of basically of that state? Because all the time you will be not given this circle things and these diagrams. Basically you need to understand what is changing. This amount of ice, the temperature of this amount of ice is changing and it is written there. So of course the specific heat capacity will be of the matter from which the temperature change is taking place, right? And for latent heat, you have to consider the matter which is basically changing its state. So these things you have to be careful. It might seem confusing, but it is not. And if you understand this scenario, basically what to use, I think the entire scenario will be very clear to you. Now you see 5 kg water which is liquid at 0 degrees Celsius is 5 kg water which is also liquid at 100 degrees Celsius. So of course Q equals to mc del theta, because temperature change is occurring and state change is not taking place. So Q equals to mc del theta, and this time this C is of water, because this amount of water is raising its temperature to this point. So this time specific heat capacity is used of water. Now 5 kg water which is liquid at 100 degrees Celsius is changing to 5 kg vapor which is gas, state change occurring at 100 degrees Celsius, no temperature change. So Q equals to ml, since it is basically boiling, so it is vapor, mlv. Q equals to mlv. So this time the latent heat of vaporization is of water. Why? Because this water is changing its state to gas. So the latent heat of vaporization will be of this water. Am I right or am I right? I know I'm right. Alright, so now that it is gas, 5 kg vapor which is gas at 100 degrees Celsius is changing to 5 kg vapor which is gas at 200 degrees Celsius. So we can see temperature changes taking place and no change of state. So again Q equals to mc del theta. This C over here is of ice. No. Then of water. No. Gas is changing. The temperature of gas is changing. So specific heat capacity of vapor. Although you don't really meet this situation that often in mathematical things. So yes, now that we are done with this whole thing, I basically have a simple question to you all. That is, we can see 5 kg ice solid at 0 degrees Celsius, 5 kg water liquid at 0 degrees Celsius. Both are at the same temperature. But my question to you is, which one has more heat? 5 kg ice which is solid at 0 degrees Celsius. Basically 5 kg ice at 0 degrees Celsius or 5 kg water at 0 degrees Celsius. Which one has more heat? Well, if you just look at the thing, I'm pretty sure when I will reveal the answer, you'll be like, it was so simple. Because you see, as I've said at the beginning of showing this, that heat is supplied to them and heat is transferred from one of the substance to the other. And in this case, I am considering that the same amount of heat is transferred. There is no heat loss to the surrounding. Now, obviously, if heat transfer between 5 kg ice at 0 degree Celsius did not take place between this one and this one, 5 kg ice at 0 degree Celsius and 5 kg water at 0 degree Celsius, then this entire, basically then this change of state would not take place. So we understand that heat transfer has occurred and change of state has taken place. Now tell me the answer, that which one has more energy? What? Both of them the same. Why? Why will both the energy be same? Because same energy is transferred? Come on, I have just said that if heat transfer is not taking place, then change of state would not occur in this situation. Which means, of course, 5 kg water at 0 degree Celsius have more energy than 5 kg ice at 0 degree Celsius, because all the energy of 5 kg ice at 0 degree Celsius have already been transferred to 5 kg water at 0 degree Celsius to change its state. So 5 kg water at 0 degree Celsius has more energy than 5 kg ice at 0 degree Celsius in this situation, because all the heat has already been transferred. It was a fun question, I know, right? I also enjoyed to ask you this question because it was a tricky one, a little. Alright, so now that we know about these things, basically we now are very well known with the entire scenario. I don't think now we are very confused with the scenario that this happens in this case, this happens in this case. We are not confused right now. We are confident that this is the entire situation. The entire situation is picturized in front of us, and we will depict the situation now. We are able to depict the situation now. Alright, so basically now I will meet you a very easy thing, that is this entire situation that I have shown you with diagrams to make it, and these equations and stuff to make it easier for you. This thing is actually represented using a graph. So you just need to be acquainted with the graph, how the graph looks during melting and boiling and all the other situations. It is basically the same, pretty same as this, but it's just graphically shown. Okay, have you ever met something like this before? You can look at it, that if you're well known with this thing or not. Alright, so what can we see? Again, we can see the graph is plotted with temperature against time. This is temperature, this is time, temperature in degrees Celsius. Okay. So once again, this is of water, because since we have worked with water till now, and the melting point and boiling point, we are very acquainted with that of water. So let's see. Basically, we can see that temperature change takes place from minus 60 degrees Celsius to 0 degrees Celsius. Until this point, temperature is changing, and the graph is also rising. Now you see, at this point when it reaches 0 degrees Celsius, temperature change does not take place, which means during this time, the ice changes to water, since there is no temperature change taking place, and this is the melting point of ice, basically water. And then again, when they are done changing the ice to liquid, basically water, then again temperature starts increasing. The graph starts increasing, and finally, when it reaches the temperature of 100 degrees Celsius, again temperature does not change anymore, and for this period of time, basically, again state change takes place, where water changes to vapor. Alright, and we also know this, that to calculate this heat, we are using Q equals to mc del theta. This is MLF, mc del theta, MLV. This is the same as this scenario, just shown graphically. And one more important thing, I can't guarantee you that this question will be asked, but suppose if it is asked that they are providing you the melting point and the boiling point of a certain substance, and they are asking you to draw a graph like this, you might remember that, oh, the graph looked like something like this, and then we will draw it like this. Yes, it will look something like this, that temperature will stay constant during the melting and boiling point. But don't always consider that, okay, basically at 0 degrees Celsius it will stay constant, at 100 degrees Celsius this will stay constant, and it will exactly look like this, the numbering and everything. And there will be basically it will stay constant at the x-axis and this thing. Don't. Alright, because as I said before, for this graph things basically, that is, state change will only occur at the melting point and boiling point of that individual liquid. So when you are asked to draw a different graph for any liquid, you have to make the markings as the melting point and boiling point of that liquid, and the temperature will be constant only at the melting point and boiling point of that liquid. So yes, since we spent so much time discussing about water till now, one last thing that I will do with water is I will basically show you a very interesting fact. I mean, I at least found it very interesting, and I think you will also do it, because I think our psychologies match a little. So how many of you have heard the fact that water has its highest density at 4 degrees Celsius? I did. I have heard it so many times, and I have always had this question, I hope you did as well, that why will water have its highest density at 4 degrees Celsius? Well, you will be surprised to know that this fact that water has its highest density at 4 degrees Celsius, it is in fact related with the expansion of water. Thermal expansion, which we studied in the first video of thermal physics. Again, we are going back to thermal expansion in fact. Alright, one request to all of you who are not sure and who are not fully confident with thermal expansion, I'll request you to please review it from my first video, because here I will not be explaining thermal expansion once again. I will just be reviewing a situation. That's it. So yes, water has its highest density at 4 degrees Celsius. Why? So basically, let me state you a fact that the expansion of water from 0 degrees Celsius to 4 degrees Celsius is irregular, and we will explore it now. So as we can see, we have different temperature markings over here: 0 degrees Celsius, 4 degrees Celsius, 10 degrees Celsius, 30 degrees Celsius. So let's start from this point. We see temperature is decreasing because it is changing from decreasing from 30 degrees Celsius to 10 degrees Celsius. So of course temperature is decreasing. So temperature is decreasing. Since temperature is decreasing, volume is decreasing, and since volume is decreasing, density is increasing. If you are not understanding what I am saying, please view the first one. I have explained thermal expansion in detail. Alright, so density is increasing. Now you see, from 10 degree to 4 degrees Celsius, temperature is decreasing, volume is decreasing, and density is increasing. Now the special part. From 4 degrees Celsius, as the temperature decreases to 0 degrees Celsius, on its way, when temperature decreases, volume does not decrease anymore. When temperature decreases, volume now increases. And since volume now increases, density decreases. So as the temperature of water decreases morely from 4 degrees Celsius to 0 degrees Celsius, the volume starts increasing and the density starts decreasing. Now let's move this journey. That is, when temperature starts increasing from 0 degrees Celsius to 4 degrees Celsius, since this is a special range of temperature for water, when temperature is increasing from 0 degrees Celsius to 4 degrees Celsius, now volume does not increase anymore. Volume now decreases. So temperature is increasing, volume is decreasing. And since volume is decreasing, density is increasing. And the rest of the thing is same, that is from 4 degrees Celsius to 10 and 30. It is temperature increases, volume increases, but density decreases. That is basically simple, but if you can observe, that is from 0 degrees Celsius to 4 degrees Celsius, the more the temperature increases, the volume starts decreasing more and more, and hence the density increases. Hence, at this point, that is, which is 4 degrees Celsius, water has its highest density at 4 degrees Celsius. So I hope you understand that water having 4 degrees Celsius, it is related with the irregular expansion of water from 0 degrees Celsius to 4 degrees Celsius. Alright, I hope it was a fun fact. I honestly did it just for fun, but I hope you got some information, new information. Alright, so please excuse me to remove this thing, and then I will actually take time to confuse you more. So wait a minute. Alright, so yes, how many of you have heard the term called evaporation before? Oh dear, all of you. I think all of you, or I guess most of you, I think everyone has heard the term evaporation. Well, evaporation is a term we are so acquainted with. Now, I understand all of us heard the term evaporation, but there is a difference between knowing something and knowing the name of something. So, until today, we have just known the name of evaporation. Now, do we actually know what evaporation is? I don't think many of us do. So, let's get started with evaporation. What is basically evaporation? At least let's just speak out. What do we actually know till now? Basically, we have faced situation where we termed is that this is called evaporation. Basically, what happens during evaporation? Liquid changes to gas. That is it. Liquid evaporates, and basically when liquid evaporates, liquid is changing to gas. That is it. Oh dear, I thought liquid changes to gas during boiling, right? Okay. Liquid changes to gas. So what is the difference between boiling and evaporation? Of course, they are not the same. Well, I will actually not move to the difference, stating this is the difference between boiling and evaporation, and then you will just memorize it. No. I will basically explain you what evaporation is, and when you understand what evaporation is, you yourself with your own intelligence can explore the difference between boiling and evaporation. So let's get started with evaporation. Alright, so evaporation is basically, I don't know. So what happens is, when we have a container, suppose we have a container containing water. Again, I'm choosing water, but it can be any liquid. Any liquid can evaporate, not always water. So, and suppose we keep a container, say containing a liquid, under the sun. Alright? And we keep it for some days. Of course, some of the water it will evaporate. Now, what is the thing that is occurring in the water in the container which makes it to evaporate? Basically, when the water in the container is kept under the sun, what happens is, the water of course in the container is gaining some energy from its surrounding, because the surrounding is heated. So the water itself, it will gain some energy from the surrounding. So what happens is, water molecules at the surface of the water is basically gaining more energy. Why? Because it is at the surface, it is more exposed to the environment. So since it is getting heat from the environment, of course the surface molecules, it will get more heat from the environment. So since the surface molecules of the water, it is gaining some more heat from the environment, what it is doing is, it tries, or it has a tendency, getting more energy, it has a tendency to overcome the downward force of attraction of other molecules. And for what and for this to take place, it also does something. It not only uses its own energy, but also takes some energy from molecules at the bottom of the container, so that the molecules of the container gets more weaker, basically less energetic. So they are already less energetic, and when more energy is taken away from them, they get like the least energetic. So in this way, when they gain so much energy, the surface molecules of water, that time basically they get able to overcome the downward force of attraction of other molecules, and they finally escape into the atmosphere. And that is what we term as evaporation, that liquid has evaporated. So when it escapes into the atmosphere, of course it is a gas. Now basically we understand this, we are listening to this scenario as a story. Basically what happens is, when itself the surface molecules, they are gaining so much energy, and they are with that amount of energy, what happens when the molecules, they get heated up? We all know that what happens, that basically their molecular movement and molecular arrangement, a change take place in the molecular movement and molecular arrangement. So getting so much heat, already a molecular arrangement and molecular movement, a change in them takes place. So when they overcome the force of attraction and escape into the atmosphere, they are actually having a lot of energy, which has already changed the molecular arrangement and molecular movement of the water molecules. So they are now no more water molecules. Due to a change in their molecular arrangement and molecular movement, they have already turned into a gas. So yes, I think we are more exploring it moment by moment, that state change is actually all about a change in molecular arrangement and molecular movement. It is not just limiting to a solid just totally changing to a liquid. Just that, it is actually related to a lot actually to molecular movement and arrangement. So yes, since we have understood what evaporation is, I think now we can actually together explore what basically is the difference between boiling and evaporation. So the boiling and evaporation, the first difference is, for boiling you need a heat source, you need to provide heat, but in evaporation they get the heat from the surrounding. Alright, second difference is, in boiling takes place basically in the whole liquid. As you have seen, the whole liquid, it changes into gas, but in evaporation it only occurs at the surface. Only the surface molecules, or the surface amount of some water, it basically changes to gas. Now the difference, another difference is, boiling actually always takes place at a fixed temperature. That's why boiling point comes. It takes place only in the boiling point of a specific liquid. But evaporation can take place in any temperature. So it does not have to take place in a fixed temperature. And one last thing is, basically for evaporation, during evaporation temperature may change, but during boiling temperature is always constant during boiling, right? Temperature is never changing. So you see, we have knowledge about boiling, we have knowledge about evaporation, and using our knowledge we can actually explore the difference. It is nothing to actually memorize that this is the difference between them. Alright, so one more thing, that is, we have heard one more fact, that is, evaporation causes cooling. How many of you did? I did a lot of times, that evaporation causes cooling. So let me basically use a very cliche example to explain you, because despite it is cliche, it is, I think, the most favorite example in O levels. So let's discuss about it. Alright, so basically this is a cliche example, that is, when a person is coming out of a swimming pool, basically when you come out of swimming pool, you start feeling cold. Why is this? So that is because the water molecules in the surface of your body, it evaporates. Now, alright, fine, it is evaporating, but why cooling? That is because when it is getting evaporated, basically it gains the energy to evaporate from your body. So, it basically gains the energy from this, also the surrounding, but it takes the inherent energy from your body and then evaporates. So since it is taking energy or heat from your body itself is losing heat, and since you yourself, your body is losing heat, that is why basically you are feeling cold. It's so simple, right? I know. Alright, So in fact, basically, when we wash clothes and we keep it to dry, sometimes in our balcony or in our roof, basically this drying process, it also occurs using evaporation. So since we know all the scenarios, let's explore the rate of evaporation. Basically, since evaporation mostly depends on environmental factors because it gains energy from the environment, let's see which environmental factor actually results in an increase in rate of evaporation, basically more evaporation. So basically, this is from our common sense. That is, if temperature is more, imagine what makes a cloth dry fastest. That is the easiest example. But yes, when temperature increases, rate of evaporation increases because temperature is more, heat is more, they are gaining more heat, so it will basically the rate of evaporation is more. Next thing is if wind speed. If wind is more, then rate of evaporation is more because wind itself blows the water molecules away from the surface. So that's why. Another thing is if surface area is more, the rate of evaporation is more because of course if the surface area is more, then more amount of molecules are in the surface, so more molecules are escaping into the atmosphere per unit time. So that is why rate of evaporation is more when surface area is more. And one last thing is when humidity is more, rate of evaporation is less. Why? Because what does humidity mean? Humidity means that there is already some water vapor in the air. So when basically water vapor is in the air basically due to evaporation. So when there is a lot of evaporation and there is a lot of water vapor in the air, that time what happens is the air itself cannot take much water vapor into itself, and that is why the rate of evaporation decreases when humidity increases. So yes, we are done exploring about evaporation. So now, as what we always do, we do a fun math when we are done with understanding most of the things. So now I will bring you the question for fun math and we will explore it together. I hope today's math will actually be fun because I'm super excited for today's math. So give me some time, I will put the math here. Alright? So yes, here I present you my question. Ta-da! You can actually look at it for a while if you want to solve it, but let's just do it together because if we do it together it's more fun. Alright, so what is our question? This is basically first our scenario and this is our question. So let's see what we have. I'm reading from here. A student investigates the evaporation of water. He pours 100 centimeter cube of water into both measuring cylinder A and B. A is kept at 40 degrees Celsius, B is kept at 80 degrees Celsius. The figure shows A and B after 3 days. So we understand that they are investigating the rate of evaporation. We are seeing that given the information that both of the water in both of the container was 100 centimeter cube before, but after keeping for 3 days in different temperature, their volume has decreased. Now basically, let's face our question. The specific latent heat of vaporization of water is 2300 joules per gram and the density of water is 1 gram per centimeter cube. During the 3 days, water level in B drops from 100 centimeter cube to 60 centimeter cube. Calculate the energy used to evaporate water from B during the 3 days. Very nice. So the specific latent heat of vaporization, so we know that our formula is Q equals to mLV. Now why? I thought Q equals to mLV was all about boiling, during boiling. But this is evaporation. Why will it be? Come on, as I said, Q equals to mL, this formula is used during state change. So it does not matter if it's boiling or evaporation. State change is occurring, so this equation will be used. Alright, so at first what I will be doing is, I will be noting down the information we have right now. So, let's see. The specific latent heat of vaporization of water is 2300 joule per gram. So basically, latent heat of vaporization is 2300 joules per gram. Density of water, density equals to 1 gram per centimeter cube. During the 3 days, water level in B drops from 100 centimeter cube to 60 centimeter cube. Calculate the energy. Alright, so our formula is basically Q equals to mLV. We have got our LV, but we need to find M. We don't have M. But doesn't matter. We are given our density, we have the volume, so we can calculate mass. So as we know, density equals to mass by volume. So mass equals to density times volume. This is our equation. We are going to find mass. Now density, we know density is given 1 gram per centimeter cube, but times what is the volume? Well, 100 centimeter cube of water was put in B before 3 days, so 100 centimeter cube, because that is the volume. No. After 3 days it was 60 centimeter cube. So 60 centimeter cube. 100 centimeter cube or 60 centimeter cube? Come on, which one? 100 or 60? 60 or 100? None of them. It is not 100 or 60. You see, we are asked to calculate the energy used to evaporate the water. So we have to find out the energy which was used for this amount of water to change into gas. So what amount of water changed into gas? The amount of water that has evaporated, right? So earlier it was 100 centimeter cube. Now it is 60 centimeter cube, which means 100 minus 60 is 40, which means 40 centimeter cube of water has already evaporated and 60 centimeter cube of water is left. So we will be writing 40 centimeter cube, and the answer will be 40 gram. Mass will be, because centimeter cube gets cancelled off. Alright, so we have 40 gram. Now we have our answers. So basically Q equals to mLV, mass is 40 grams, LV is 2300 joules per gram. Gram gets cancelled off. If you calculate, the answer will be 92,000 joules. This is the amount of energy needed for the used to evaporate water from B during the 3 days. Alright, so we are done with the fun math. I was actually excited for this specific fun math because I found it super fun. Alright, so since this was done, we are done with the fun math. What I do at the end is I always bring you a gift for those who have watched my, oh dear, 52 minutes is already done. So almost 53 minutes. Okay, so whoever have watched me till now, this is a gift for you. So this is as always, I have bring in an MCQ from the O-level physics paper. So let's do it. What happens when liquid is being heated at its boiling point? Option A, an increase in molecular size. Option B, an increase in molecular spacing. Option C, an increase in average kinetic energy of molecule. Option D, an increase in total number of molecule. So I hope you are done. What is the answer? Number C. What is C? An increase in average kinetic energy of molecule. I'm sorry, the answer is number B, an increase in molecular spacing. Well, why is it not C and B? This is because if you actually view my first or second, I'm not sure, but about simple kinetic theory of matter, that chapter's video, you will find out the relationship between temperature and kinetic energy and all this. So basically, during boiling, temperature stays constant. So of course the kinetic energy will not change, because when temperature increases, kinetic energy increases. So during boiling, temperature is constant. Hence, kinetic energy is not changing. Now, when it has already turned to gas, that time it has high kinetic energy. Why? Because of its different molecular movement. But during when it is at boiling point, during the process is occurring, there is a change in molecular arrangement. So there is nothing to do with molecular movement. So this is something you have to understand, that during the boiling process, temperature is staying constant. So there is not increase in average kinetic energy. Kinetic energy comes when temperature is increasing, or when we will deal with the kinetic energy of gas. That is because of its movement. But when it is already a gas, not when a liquid is being heated at its boiling point. So the answer is number B, an increase in molecular spacing, because when liquid is heated at its boiling point, molecular arrangement is changing. So since gas molecules, they are far apart from each other, the molecular spacing is increasing. So with that, we are also done with our MCQ, we are done with our fun math, we are done with a very interesting chapter, melting and boiling. And so yes, I will be soon done with thermal physics. Only one more chapter left, and I can just give you a hint that that is the most popular chapter, not only in thermal physics but in entire physics. So yes, with that I am done. So thank you all, thanks for listening for so long, and yes, stay home, stay safe and stay cool. Thank you so much.